Welcome back. We're ready to move on to Chapter 17. I've put up a few summary slides from Chapter 16 here, and I just want to focus on the electric field again and bring forward some ideas about the electric field. The electric field we defined in Chapter 16 as the force per unit charge, and we wrote it quantitatively here, E equals F over Q. We can rearrange and solve for force as well, that the force equals the electric field times the charge. I actually brought back a slide from Chapter 16. I added a positive negative charge here so we could remember the electric field goes from positive to negative. It starts at positive charges, ends at negative charges. And I want to remember the difference between putting a positive charge and a negative charge in an electric field. If we throw a positive charge in the electric field, it has a force that acts on it in the direction of the electric field, and that can make sense. Either you can think of it as being repelled by the positive charge the electric field starts from, or attracted to the negative charge the electric field is going to. Either way, that positive charge will have a force in the direction of the electric field. In contrast, a negative charge dropped in an electric field will have a force on it in the opposite direction. And you can either think of it as being attracted to that positive charge the electric field originates from, or being repelled from that negative charge the electric field is heading towards. But either way, you get a force in the opposite direction of the electric field. All right, a couple more summary slides, and we can begin Chapter 17. The topic of Chapter 17 is electric potential, and we'll delve right into that. Our starting topics are electric potential energy and potential difference, and then the relation between electric potential and the electric field. The later topics I'm saving for later videos. All right, let's start with the chapter opening question. When two positively charged small spheres are pushed towards each other, what happens to their potential energy? We don't know anything about electric potential energy yet, but we do know about potential energy in general, or if we took the first half of the course, and that is that there can be gravitational potential energy and electric potential energy. So let's try to relate the concepts. If we think about gravitational potential energy, let's say we have a rock. If we lift the rock, we do work on the rock, we've increased its potential energy. If we drop it back down, it has a relative decrease in potential energy. So that's one example. Or if we go to a spring, I have a little spring here, if I push on the spring, then again I'm doing work and I'm increasing the potential energy of the spring. All right, so let's think now about the charges, and let's think about two positive charges. So our positive charges in our text are red, so I have two little red pieces here. And if I push them towards each other, what happens to potential energy? Well, we have to remember that likes repel. So these two positive charges feel forces on each other that push them apart from each other. So if I push the two spheres towards each other, I can expect that that takes effort on my part, and that will result in an increase in the potential energy. So I would guess that there will be an increase in potential energy, and we'll come back to that later. Section 17.1 is titled Electric Potential Energy and Potential Difference. That's quite a mouthful. Let's start with the first term, electric potential energy, and that's actually, we sort of touched on that already with our opening chapter question. So electrostatic force, the force in an electric field, or electrostatic force, is a conservative force. So it's similar to gravity in that it's a conservative force, and one of the things that means is it doesn't depend on the path taken. Friction, if you recall, was dependent on the path. Our gravitational force didn't depend on path, and similarly for an electrostatic force, it's independent of the path taken. You just care about your starting point and your ending point and how much you've changed in your position, say, along an electric field line. All right. For a conservative force, a potential energy can be defined. Just like gravitational potential energy, we can talk now about electric potential energy. And just like gravitational potential energy, it's the changes are what matter, not the absolute amounts of potential energy, but relative values. All right. So a change in potential energy was defined back in Chapter 6 in our chapter on work and energy as being the negative of the work done by the force, and the that corresponds here that for the change in electric potential energy, that's the negative of the work done by the electric force. So let me start out quantitatively. From chapter 6, we have work equals force times displacement. And from chapter 16, we know the force on a charge is E times Q. That was the equation I just reviewed. So for force here, we can drop in for electrostatics, QE here. So the work done to move a charge from one position to another equals Q, the amount of that charge, E, the strength of the electric field, and D, the distance we move it along an electric field line. So that's our work. And we said the change in potential energy is the negative of the work done. So our change in potential energy here, potential energy at point B and point A, say for some charge moving between two positions, is equal to the negative of this work, negative QED. All right, so that gives me some equations to work with later in the chapter. Let's think now a bit more conceptually. And we have a view here of this gray region to the left is a positively charged plate. So there are all these little pluses can stand for excess positive charge. Then this gray vertical bar to the right is a negatively charged plate. And there are all these little dashes here for negative charges. So say excess electrons there. Electric field goes from positive to negative. So it goes uniformly across this region between the positive and the negative plate. So we get a uniform electric field here. All right. Mentioned the word electric potential a few times so far. Anywhere where we move up an electric field line, we're going to regions of high potential. And if you have a positive and negatively charged plate, the positive plate always has high potential. Another word for your potential is your voltage. So a region of high potential is a region of relatively high voltage. And then if we move to the right here, we move down the electric field line, we move to a region of relatively low potential or low voltage. Now let's drop a charge here. We'll talk about potential energy. And notice that word is showing up repeatedly. Potential for voltage V and potential energy, and they're different. The potential energy will depend on the sign of the charge. And we start out just as we did in chapter 16. Everything's defined in terms of positive charge. So we drop a positive charge into our electric field. Let's say we drop it here at position A near the positive plate. We know if we put two positive charges near each other, they're going to repel. That's a region of relatively high potential energy. If we move the charge down here to position B, then it's close to the negatively charged plate. A positive charge would, under natural forces, will move towards the negatively charged plate. So that is a region of relatively low potential energy. That's where the charge would be moved to if the electric field is allowed to move the charge. That's the direction it'll move in. All right, so what do we see? We see for a positive charge, if it's in a region of high potential, it experiences high potential energy. If it's in a region of relatively low potential, it has relatively low potential energy. All right, let's consider now gravitational potential energy so we can try to relate these ideas to something that's a little less abstract. All right, so let's go back and recall chapter 6 was the chapter on work and energy, and this slide I've pulled from that chapter where we looked at the work done on a backpack as it was moved by a hiker uphill. All right, so the first thing I want to remember is that equation for change in potential energy, and that was mg delta H. And one thing I want to point out is the delta H just had to do with the vertical height that we changed. So it was independent of path taken again. It didn't matter if we went in a circuitous route, if we went straight up a ladder, if we went downhill and uphill. Our change in potential energy, we just had to care about our starting position and our ending position and how much vertical change that was. So delta H was a vertical change, and that's the direction of gravity as well. Okay, so that's our change in potential energy. The other thing I want to talk about is whether the work done is positive or negative, and that depends on which force is doing the work. So the first thing we consider is, say, the work done by an external force, say the backpacker, the hiker. So the work done by the hiker to go up the hill, we know the hiker is doing work against gravity. There is an effort for them to go up the hill. And indeed, the work done by the hiker on the backpack is positive. And you could review this back from chapter 6 if you want to. But the work done by the hiker on the backpack, in this case it was 1470 joules. In contrast, what's the work done by gravity? Well, gravity does not help us bring the backpack uphill. We're doing work against gravity. So the work done by gravity on the backpack was a negative amount. So negative 1470 joules. They were equal in magnitude but opposite in sign. All right, I want to consider these ideas again, but I want to change my picture from the picture of a hiker in a backpack. I want to go a little more abstract and something that will have a closer parallel to electric potential energy, where we're headed. All right, so here's my image. I've got a lower location here. I've got a higher location here. So you might consider this blue bar as, say, the floor of a room, and this blue bar is the ceiling of a room. I'm going to move, say, it's kind of like a tin can to me. I'm going to move it from position A to position B. The gravitational field is present here. It's going vertically downward. So that's our gravitational field. And if I'm going to move the can from A to B, and I'm doing this, I'm exerting, I'm an external force, and I'm taking it from a low position to a high position. That takes work for me to do that. So indeed, the work done by the external force is positive, as shown here. Work equals plus mgh. The work done by gravity, gravity doesn't help us here. We're doing work against gravity. So the work done by gravity, the conservative force, is minus mg delta h. Okay, what about potential energy? When we're in a lower position, we have relatively low potential energy, or the can does. If we move it to a high position, it has relatively high potential energy. All right, so that's our review. Now I want to recast this and have a fairly similar diagram, but have it be in terms of our electric field and electric potential energy. So that's here. And again, we'll start with a positive charge. And we have our two blue bars again, but now the positive bar is a positively charged plate, and the negative bar is a negatively charged plate. On the positively charged plate, we have all this excess positive charge. It's a region of high potential, or what we're going to call high voltage. And then the negatively charged plate is a region of relatively low potential, or low voltage. Okay, the electric field goes from positive to negative, so it goes downward in this image from the positive plate to the negative plate. So there's our electric field. So far everything is the same as for our gravitational example. The difference is, instead of having some mass to move from A to B, we're going to have a charge, and we have two types of charge. So we're going to start with a positive charge, and we're going to move it from this region of low potential to this region of high potential. All right, so let's consider that. We have our positive charge, and if we're going to try to bring it closer to the positive plate, and let's say we are an external force and we're trying to move this charge towards a positive plate, towards, say, positive charges, that's going to take work for us to do that. So the work done by the external force is a positive QED. What about the conservative force, or the electric field? The electric field isn't helping us here. The electric field would move the positive charge in the direction of the electric field towards the negatively charged plate. So the work done by the conservative force is going to be negative. So the work done by the conservative force of moving a charge towards the positive plate is negative. Okay, what about potential energy? Our positive charge, when it's near the negative plate, that's where the positive charge would naturally move towards. So that's a region of relatively low potential energy. You try to bring that positive charge towards the positive plate where it's going to be strongly repelled, likes repel. That's a position of relatively high potential energy. So what do you notice? We notice for a positive charge that there's a correspondence that if you're in a region of relatively high potential, a positive charge will have high potential energy. If you're a region of relatively low potential, your positive charge will have relatively low potential energy. All right, let's move on to a negative charge in the electric field. So everything's the same here as it was before, except now we have a negative charge that we're moving from A to B. So we still have a positive and negatively charged plate. A positively charged plate still has relatively high potential, high voltage. A negatively charged plate is still relatively low potential, low voltage, and the electric field goes from positive to negative. That's all the same. So what happens if we try to move a negative charge towards the positive plate? Well, that's just what the electric field wants to help you do, is move a negative charge towards the positive plate. A negative charge will experience a force in the opposite direction of the electric field, so right towards that positive plate. And you can also think of it in terms of negative charges attracted to the positive plate. So the electric field helps us to move the negative charge towards the positive plate. So the work done by the conservative force, the electric field, is positive, as shown down here. work equals plus QED. Whereas the work done by an external force, we don't have to do work. If we had a hand here trying to move this charge towards the positive plate, we don't have to do that. It will naturally move in that direction under the influence of the electric field. So the work done by the external force is negative. All right, what about potential energy? Well, when that negative charge is near the positive plate, that's where it's attracted towards. That's a position of relatively low potential energy. When the negative charge is near the negative plate, it's strongly repelled by that negative plate, that's the position of relatively high potential energy. So in the case of a negative charge, our potential and potential energy do not correspond. If you're in a region of relatively high potential, a negative charge has relatively low potential energy. If you're a region of relatively low potential, a negative charge has relatively high potential energy. All right. So let's go back to our chapter opening question. When we had our two spheres and we try to bring the positive charges closer together, I brought forward our image here for a positive charge. The positive plate isn't exactly a single positive charge, but the behavior will be the same. If you bring a positive charge towards the positive plate, that is indeed going to be a region of higher potential energy, and so the potential energy of the two charges, if it's two charges that are being brought closer together, does indeed increase, as we had guessed at the start of the video. All right, so let's go a bit more quantitatively into these ideas. So we had electric potential energy, so that's what we just talked about. Now we're going to talk about electric potential and potential difference. I threw this electric potential in there because that's a third term with the word potential. So what is electric potential? That term I threw in there. Electric potential, say at a position A, is defined as the potential energy per unit charge. You can compare that to electric field, which is the force per unit charge. The potential, or the voltage, is the potential energy per charge. The unit of electric potential is the volt, and one way of defining volt is a joule per coulomb, which falls right out of this equation. Units of energy are joules, and units of charge are coulomb, so the unit of volt is a joule per coulomb. All right, another potential confusion here is we have two V's on this page, on this slide, and they mean different things. We have one V for our variables, and this V stands for potential at point A, and we represent potential with the letter V. The second V stands for our units, and we represent the unit for potential, which is the volt, also with a V. So we want to be aware of that as well. Okay, similar to gravity, we never talked about how much gravitational potential energy had, say, a rock or a amusement park ride, a roller coaster had on its own. We're always comparing our gravitational potential energy. And we could decide wherever we want to, we could make equal to y equals 0, our zero position for potential energy. And the same thing is true for electric potential. It's only changes in electric potential are physically meaningful, so we can freely assign our position where our voltage is, or our potential is 0. So we can define our change in potential between 2 points A and B as the potential at point B minus the potential at point A. Remember the previous slide, our potential at say point A was potential energy divided by Q. So the difference in potential is the difference in potential energies at B and A divided by Q. And from that very early slide for this chapter, we already went through that the change in potential energy is the negative of the work done. So we can drop that in. Change in potential energy, we can drop in negative of the work done. And now we have a definition for the change in electric potential. The change in potential between points A and B is equal to negative of the work done to bring a charge from A to B divided by the magnitude of that charge, Q. Our units of electric potential difference is the same as our unit for electric potential, because all we did was subtract two potentials. There wasn't any difference in the unit, it's still the volt. The units for volt is still a joule per coulomb. And our units for work are joules, and of charge are coulombs, so that all holds nicely. Let's try a problem. So how much work does a uniform electric field do to move a proton from a point with a potential of plus 125 volts to a point where it is minus 55 volts? We're asked to express our answer in joules. So what I want to do, I want to sort of pick out what my key ideas are here so I can figure out what equation to use. I'm also going to draw a picture that represents moving a proton from an area of high potential to lower potential. So we're asked to figure out how much work is done on a proton, so that's a certain amount of charge, when it goes through a difference in potential. This equation up here gives us a difference in potential is equal to the work done divided by the charge. That plays with all the variables I have in my problem. So I'll have to rearrange to solve for work, but that equation looks like a good place to start. Then I want to think conceptually about what's actually being done in this problem. So we're moving a proton, so that's a positive charge, from an area of high potential, so position A is going to be high potential, to a position of relatively low potential, position B. And I'm going to define position A as being plus 125 volts and position B as being minus 55 volts. And one way you could have a change in potential would be to have, say, two parallel plates of different charge. We're going to go from high potential to low potential here. So that gives us a bit of a cartoon version of how we can think about moving a proton from an area of high potential to relatively low potential. We're asked to solve for the work, so we'll rearrange and solve that the work to go from position A to B is the negatives that change in the potential from A to B multiplied by the charge. Charge was the charge on one proton. The charge on one proton equals the charge on one electron, 1.602 times 10 to the minus 19 coulombs. Okay, and so what's our change in potential? The change in potential from A to B, we always take final minus initial, just like we did in, say, displacement and many other examples last term. So we take our final potential minus our initial potential here for our change in potential. So potential at position B minus potential at position A times Q, our charge. And we bring down that negative sign. All right, now we very carefully watch our signs. Our potential at position B is minus 55 volts, so we drop that in. Our potential at position A is plus 125 volts, so we drop that in for VA. But there is a negative in that parenthesis, so it's minus 125 volts. Even though the starting potential is plus 125, there's a negative there in the equation. And then our charge is the charge on a proton, so we bring that in. First, I'm going to evaluate what this value is. Minus 55 minus 125 is going to be minus 180 volts. And so we might want to check and make sure that makes sense. We start from 125 volts. We're going from 125 volts down to 0, and then into the negative range down to minus 55 volts. So our total change in potential does indeed go through 125 to 0, down to minus 55, or a total drop of 180 volts. So that's what we see here, a drop or a decrease, a negative 180 volts. We still carry down that negative sign from the equation. We have our charge on the proton. We run all that through a calculator, and we get about 2.88 times 10 to the minus 17 volt times a coulomb. So that's looking pretty good, but a volt times a coulomb isn't a unit of work that I'm familiar with. But if we consider what we just said, our equation for a volt is a joule per coulomb, or a unit of volt is a joule per coulomb, then we can rearrange that, and a joule is a volt per coulomb, so we replace that. And we get the work to go from A to B is 2.88 times 10 to the minus 17 joules. All right, we can make another analogy between gravitational and electric potential energy. If we consider that if we increase the amount of mass that we hold at a certain given height, we have an increase in potential energy, because the potential energy is mgh. If we increase our mass, we'll have an increase in gravitational potential energy. Similarly, if we look at our electric potential energy, if we increase our amount of charge, we'll have an increase in electric potential energy. So if we go from a charge of Q and double that to 2Q, we'll have an increase in the electric potential energy at that position. All right, let's put voltage into some perspective with some ideas that we are more familiar with. Let's start with, say, a flashlight battery. The flashlight battery has 1.5 volts of potential. So what that means is between the positive and negative terminal, we have a 1.5 volt potential difference. All right, some other familiar voltages. A car battery is about 12 volts. A household outlet is 120 volts, or about 100 volts. This is order of magnitude. And we can move up to things with higher potential, all the way up to the potential that a lightning bolt bridges when it goes from cloud to ground, which is about 10 to the 8 volts. All right, if we go to smaller values, we get to some biological applications. The resting potential across a nerve membrane is about 1/10 of a volt. Potential changes on the skin measured by an EKG or an EEG is about 1/10,000th of a volt. All right, what I want to talk about now is the relationship between electric potential and the electric field. The effects of any charge distribution can be described by either the electric potential or the electric field. But electric potential is a scalar, whereas electric field we saw was a vector. It had magnitude and direction. So for problem solving, electric potential is often easier. All right, so let's look at a few ideas here. Work is charge multiplied by potential. So we already knew that potential was work per charge, so we can rearrange that and solve for work. So work is equal to the negative of the charge times the difference in potential from A to B. Work is also, from chapter 6, is force times displacement, and the force on a charge in electric field is equal to the amount of charge times the electric field. That's F equals QE. If we combine these equations together, we can solve for the uniform electric field E, and we can get that is equal to the negative of the change in potential between A and B divided by the distance D, where distance D is measured parallel to the field line. So similar to gravity, where we measure displacement vertically in the direction of the gravitational field, our D here has to be measured in the direction of the electric field. All right, so we now have this new equation for a uniform electric field. It's equal to the negative of the change in the potential between points A and B divided by D, where D is the distance between A and B that's traveled along an electric field line. All right, from chapter 16, we already had an equation for uniform electric field, and that was that it was equal to the force per unit charge. So we now have two equations to describe a uniform electric field. And we can use either one depending on the application. With such different variables here, you'll notice that they're different units. For our first example, our units of potential are volts and distance are meters. So the electric field is units of volt per meter. And our second equation here, our units of force are newtons and of charge are coulombs, so our units are newtons per coulomb. They're both equivalent. We could go through and do some units conversions and show that a volt per meter is indeed the same as a newton per coulomb. All right, let's try another problem. Let's find the uniform electric field between two parallel plates connected to a 45-volt battery, and we're told it's 1500 volts per meter. How far apart are the plates? So let's begin by drawing ourselves a little diagram and considering what equation would be appropriate here. What do we know? We know that we have an electric field is 1500 volts per meter between two parallel plates connected to a battery source, 45-volt battery. So I've drawn my first electric circuit here. This is a schematic version. This is more of a how we'll tend to simplify things for an electric circuit. But our schematic version is a good place to start. We have two parallel plates, a positive plate and a negative plate. We've never talked about how we can get two parallel plates with different charges, but way to do that is connect it to a battery. So we connect two parallel plates, positive plate to one terminal of the battery, the negative plate to the other terminal of the battery, and the plate connected to the positive terminal of the battery will become positively charged, and the plate connected to the negative terminal becomes negatively charged. But we end up with two parallel plates, one with charge plus Q and the other with charge minus Q, and there's going to be a uniform electric field between them going from positive to negative. All right, so we have a uniform electric field between two parallel plates connected to a 45-volt battery as shown here, and the field in there between the plates is 1500 volts per meter. We want to know how far apart are the plates. That would be our distance D. All right, so we have an equation that electric field is the negative of the potential between points A and B divided by D, that distance, or we can rearrange that D is the negative of the potential divided by the electric field. One point I want to make is that D has to be in the direction of electric field, but our electric field goes directly from, say, the positive charge to the negative charge, directly across that gap. So the distance between the two plates is the distance along the electric field line, so that D is appropriate. All right, so we have our values here. It's the negative of the potential, and the difference in the potential between these is the potential provided by the battery, minus 45 volts, and the electric field is between the plates is 1500 volts per meter. So we put that in for our electric field, and we can solve for D, and we get, in this case, a minus 0.03 meters. So the value seems reasonable, a fraction of a meter. The negative doesn't make sense. We can't have a negative distance here. But if you think about it, our distance here from A to B is the same as our distance from B to A. So we could just reverse this. We can get rid of that negative sign, and we'll get a positive value for distance. So sometimes we do get phantom negative signs, but we can make sense out of that. Okay, so we correct that, and we get a distance there of 0.03 meters, and we're done. All right, I want to stop there. That's a lot of material to start the chapter. We'll pick up with section 17.3 in the next video. See you then.